Absolute age. Number 1. Absolute age determines the age of fossils, rock layers, and igneous intrusions in terms of years. This is done through a process known as radiometric dating. 2. Chemical elements may have unique forms called isotopes. Each element has a specific number of protons. Isotopes have different numbers of neutrons but have the same number of protons. So carbon-12 would have 6 protons and 6 neutrons. Carbon-14 would still have 6 protons, but has 2 extra neutrons, has 8 neutrons total. Number 3, these elements, known as isotopes, have extra neutrons. They may be unstable or radioactive. A, they naturally break down into a different element called its decay product. B, carbon-14 breaks down into nitrogen-14. On the Earth Science Reference Table, on the front page, you'll find information on the radioactive decay for 4 specific elements: carbon-14, potassium-40, uranium-238, and rubidium-87. Carbon-14 changes into nitrogen-14. Potassium-40 changes into argon-40 or calcium-40. Uranium-238 changes into lead-206. Rubidium-87 changes into strontium-87. Number 4. Amongst radioactive isotopes, decay occurs randomly among a group of atoms. However, the rate at which it occurs is reliable. A, it is not affected by heat, pressure, or any means known as of yet. 5. Half-life is the time it required for half of the atoms in a sample to change to decay product. For example, carbon-14 has a half-life of 5,700 years. If I had 1,000 grams of carbon-14 at the end of 5,700 years, out of that 100 grams, only 50 will remain radioactive. That's why it's called a half-life, the number of years it takes for the sample of isotopes to become half. Potassium-40. Potassium-40 has a half-life of 1.3 billion years. Uranium-238 has a half-life of 4.5 billion years. Rubidium-87 has a half-life of 49 billion years. Half-life is the time it requires for half of the atoms in a sample to change to decay product. To determine the age of substances, it's useful to devise a chart. The chart might look something like this. On the chart, it will list half-life, years, the radioactive isotope that you're using, and the decay product, whatever the isotope turns into. For my example, I'm going to use carbon-14. Let's switch from this chart here to this chart here. On the chart here, we can see half-lives, up to 10 half-lives, number of years, the amount of atoms of carbon-14, and the amount of atoms of nitrogen-14. If we had 100,000 atoms of carbon-14, there were 100,000 atoms of carbon-14 starting off at present time, we'd have 0 half-lives. Not enough time has gone by for the atoms to decay, and we'd have 0 nitrogen-14. 5,700 years later, the reference table gives us that value for carbon-14's half-life. The 100,000 atoms of carbon-14 will have decayed to 50,000. During that time, what will be produced is nitrogen-14. And since we started off with 100,000 atoms of carbon-14 and only have 50,000 atoms of carbon-14 now, we know that 100,000 minus the 50,000 gives us 50,000 atoms of nitrogen-14. So after one half-life, 5,700 years, we have half the original amount, and we figured out how much decay product we have. At 2 half-lives, another 5,700 years has passed. To calculate the number of years, I'm going to take the 5,700 plus another 5,700 years. At 2 half-lives, we're at 11,400 years. Now, since one half-life has passed, if we had 50,000 atoms to start off with, now we have half of that amount. I now have 25,000 atoms of carbon-14. How much nitrogen-14 do I have? I started off with 100,000 atoms of carbon-14. I now only have 25,000 atoms of carbon-14. If I take 100,000 minus 25,000, that equals 75,000. One way that I can know that I am correct in the number of atoms that I have for this column is adding these two numbers together should equal the original amount of atoms I had, which was 100,000. To determine the number of years that have gone by for 3 half-lives, we're going to take the 11,400 and add another 5,700. That gives me 17,100 years of time. To determine the number of carbon-14 atoms I have, I'm going to take 25,000 and divide it by 2, and that gives me 12,500. To determine the number of carbon-14 atoms, I'm going to take the original amount of atoms I had, which was 100,000, minus the amount that I have right now, which is 12,500, and I get 87,500 atoms. Now, to figure out the number of years for 4 half-lives, I can take this number and add 5,700. Another way to do that is I can also multiply 4 times 5,700. After 22,800 years, the number of carbon-14 atoms can be determined once again. We'll take the amount we had before, divided by 2. And to figure out the number of carbon-14 atoms, we take the original 100,000 atoms, subtract 6,250. We now have 93,750 carbon-14 atoms. To figure out the number of years for 5 half-lives, we can either add 5,700 to this, or we can take 5 times 5,700. To figure out the number of atoms of carbon-14 we would have now, we take 6,250 divided by 2. To figure out the number of nitrogen-14 atoms we have now, we had originally 100,000 atoms of carbon-14. We subtract 3,125 from that, gives us 96,875. What your assignment is to complete the chart. To figure out the number of years, you can multiply 5,700 times the number of half-lives to get that, or just add 5,700. To figure out the number of carbon-14 atoms, you just divide the number in half. To figure out the number of nitrogen-14 atoms, take the number of carbon-14 atoms you now have, subtracted from the original amount, draw a line graph showing the amounts of carbon-14 and N14 through 10 half-lives. At 0 half-lives, we had 100,000 carbon-14 atoms. After one half-life, the number of carbon-14 atoms dropped to 50,000. After 2 half-lives, the number of carbon-14 atoms dropped to 25,000. After 3 half-lives, the number of carbon-14 atoms dropped to 12,500. After 4 half-lives, 6,250. After 5 half-lives, 3,125. Part of your homework is to complete the graph at the bottom and to draw a line that connects the values of carbon-14. Please continue out to this section. On the graph, we also need to plot nitrogen-14. At 0 half-lives, the amount of nitrogen-14 is 0. At 1 half-life, the amount of nitrogen-14 is 50,000. At 2 half-lives, the amount of nitrogen-14 is 75,000. At 3 half-lives, the amount of nitrogen-14 is 87,500. At 4 half-lives, the amount is 93,750. At 5 half-lives, it's 96,875. Your assignment is to continue to plot the graph and to fill in the information table. Half-life is the time it required for half of the atoms in a sample to change the decay product. So at 0 half-life, we have 100% original material, 0 decay product. After 1 half-life, we have 50% of the original and 50% of the decay product. After 2, we have 25% of the original, 75% is decay product. After 3 half-lives, we have 12.5% of the original, 87.5% decay product. After 4 half-lives, we're at 6.25% of the original, 93.75% decay product. After 5, we'll have 3.125% of the original and 96.875%. So we keep on making this half of what it has. So theoretically, if we keep on splitting something in half, the number will get smaller, but actually it will never reach 0. So theoretically, a substance will never become completely radioactive free. As this line gets lower, it gets closer to 0, but it never hits 0. As this line gets higher, it gets closer to 100%, or in this case 100,000 atoms of nitrogen-14, but it never will hit 100,000.